Hello everyone, my name is Vijay Kumar and we are studying refrigeration and air conditioning. In the last video, we have studied about the duct system. After that, we have seen pressure loss in a duct due to friction. After that, we have seen the equivalent diameter of a circular duct for rectangular duct. Now in this video, we will study about the duct sizing methods. What is the meaning of duct sizing method? The duct sizing method tells about the size of a duct. How much size of a duct we have to select for a system. There are three methods: velocity method, then equal friction method, after that static regain method. First we will see velocity method. Before study the velocity method, first we will see friction chart. What is friction chart? Friction chart is drawn between air volume and friction loss. In this, air volume is measured in cubic feet per minute and friction loss is measured in inches, H2O per 100 feet. This is the friction chart. There are vertical lines which are the constant friction lines or constant pressure loss line, and these are the constant horizontal line. These are the constant air volume line. And you see here, these are the inclined line, this one, and this one. These are the duct diameter line. You can say these lines are showing the duct diameter. That means duct size they are showing. And these lines are the showing the velocity of air in the duct. Velocity of air in the duct. This is the friction chart. Let's see the velocity method. First, the velocity method is also called the velocity reduction method. Okay, so the velocity reduction method can be used when sizing air duct. The methods can be summarized to: first, the process in velocity method is that this is the first process. What we have to do: select suitable velocity for main and branch ducts from the table below. Friends, you know very well, in a duct system, from the air equipment, the main duct will flow, and through that main duct, then air will distribute to the building. And after the building, the duct or air will flow into the rooms, individual rooms. That means the duct which is coming from the air conditioner equipment, that is the main duct. And the duct which is flowing into the building, that is branch duct. And main branch duct, you can say, that is the main branch duct. And what is the branch duct? The branch duct is that which is giving the air into the room, individual room in a building. That is the main branch duct. So we have to select the velocity for main and branch duct from the table below. So this table we have to see, and we will select the velocity. Before selecting the velocity, we have to consider these 3 points and this one also, because we have to see for which system we are selecting the velocity. Either it is a comfort system or industrial system or high speed system. We have to check on these 3 parameters and on these 3 parameters. Accordingly, we have to select the velocity. This is the first step. Now, find the size of the main and branch duct from the air flow rate and the velocity by using the equation below. This is the second step. In the second step, you know the equation Q is equal to area into velocity. In this step, we know the air volume flow rate. This is given. This is given, and velocity we have selected from this table. Now from this we can calculate area is equal to Q by V. And what is the A? A is the duct area, and Q you know, and V is you also know. Okay, from this we can calculate the area. Now from the velocity and duct dimension, from the velocity which we have selected and the duct dimension which we have calculated in step number 2, find the frictional pressure loss in the main duct and branch duct using the friction chart. Let's see. Suppose we know the air volume flow rate and we have selected some velocity. Suppose we have selected, if I say, suppose we have selected this one, or if I say suppose this one, 400 fpm. Suppose we have selected the velocity in a main duct, this is 400 fpm, feet per minute. Now after calculating, and this is the given the air volume flow rate, this is 90. Suppose if I say 90 is given air volume flow rate. So at this point, if I calculate the diameter, then I'll get the diameter 6 inches. 6 inches will be the duct diameter. That will be the duct diameter. Okay. By using this friction chart, I can calculate the duct diameter. Accordingly, what is the pressure loss? In this case, if I draw a vertical line at the bottom, vertical line like this, so accordingly I'll get the frictional pressure loss. Okay, so this is the method of velocity reduction method, through which we will calculate the frictional losses or frictional pressure losses in a main duct or branch duct. Now in fourth step, add minor or dynamic losses. You can say there is a minor losses, like there is a sudden bending in the duct, that is minor loss. There is a sudden contraction, there is a sudden expansion in a duct, this is also the minor losses. Okay, so we will add all these minor losses in the frictional pressure loss, which we have calculated at step number 3 from the frictional chart. Okay, now the velocity method is one of the simplest way of designing the duct system for both supply and return air. I think no problem in that. However, the application of this method requires selection of suitable velocity in different ducts, which requires experience. This is very important part from the velocity reduction method. Friends, listen very carefully. You know very well that Q is equal to area into velocity. Here, area is equal to Q by V. If velocity, you have selected very high velocity. If you have selected very high velocity, then you will get the area very less area, that means very less diameter. And if you have selected very less velocity, then you will get the diameter very high. That means size of the duct will be very high. Okay, what will be the effect of both the condition? Let's see. Wrong selection of velocity can lead to very large duct. So in this case, we have selected the velocity very less. Because of that, diameter of the duct or size of the duct will increase, which occupy large building space and increase the cost. So this is not desirable. Now in the second case, if you select, there is a very small duct which lead to very large pressure drop and hence necessitate the selection of a large fan, leading to high fan cost and running cost. If you are selecting the velocity very high, in that case size of the duct will be less. Because of the less size, diameter of the duct will be less, and there will be a high pressure loss. So to counter or to overcome that pressure loss, size of the fan we have to increase. Because of that, cost of the fan will also increase. This is also not desirable. So because of these two reasons, it requires experience. So much experience you require, friends, to select the velocity. And now, in addition, the method is not very efficient, as it requires partial closing of all the damper except the one in the index run, so that the total pressure drop in each run will be same. In this case, we have to maintain the low total pressure drop in each run same, but it is not possible. So it is not efficient. Why? Because how you have to maintain the total pressure in each run same with the help of damper. Now every time you have to damper close, partial close. By partial closing the damper, you will reduce the pressure. Okay. Because of that, there will be a very major losses. Because of that, losses will increase. If losses increase, then it is not a very efficient method. So friends, this one is the velocity reduction method. There is no numerical in this topic. You have to just remember the concept, what is this method is saying. So friend, this is the velocity method. Let's see what is equal friction method. Now in equal friction method, the design method, it is the friction design method sizes the duct for a constant friction rate, which describe the average pressure drop per 100 feet of duct in a system. What is the meaning of this? What is the meaning of this constant friction rate? The meaning of it is this, that friends, that the pressure in this duct, pressure loss in this duct, pressure loss in this duct will be same. This is saying the equal friction method. This is the brief which I have told you. In this case, whatever pressure drop in this line, whatever pressure drop in this line, and whatever pressure drop in this line, all these three pressure losses, we will assume that they all are constant and they all are same. This is the equal friction method. This is the brief. Now, equal friction method uses a duct slide rule, duct calculator, or duct friction chart. Friction chart rate. There are different rules like duct slide rule, duct calculator, these are not in your syllabus, or friction rate chart that I have already explained. That is the friction chart only to determine the relationship between the duct size and airflow. How much airflow will come out of the given size of the duct? Okay, the methodology is as follows. First, compute the necessary air volume flow rate in each room and branches of the system. Like this, there is a system. Suppose this is one room, this is second room, and this is third room. In first room, air volume flow rate is x1 meter cube per second, or x1 CFM you can say. In this, it is x2 CFM, and in this room, suppose it is x3 CFM. Now, use this one to compute the total air volume flow rate. What is the total air volume flow rate from this pump you can say, or compressor? That will be x1 plus x2 plus x3 CFM. Okay. Now, I have calculated the total CFM we got in this duct. This is the main duct you can say, and this one is the main branch duct, and this one is the branch duct. Now I think it is clear. Now you got the total CFM. It is x1 plus x2 plus x3 CFM. And from the velocity reduction method, we will select the velocity for this duct also. Now in this case also, we are using the velocity reduction method. Now we got the air volume flow rate. We selected the velocity. Accordingly, we will calculate the diameter. And according to that diameter, we can calculate the pressure loss also. So in this case, in equal friction method, whatever pressure loss in this line, whatever pressure loss in this line, whatever pressure loss in this line, we will assume that in all the lines or all the ducts system, it is same. Now you can see here, determine the major pressure drop in the main duct. Now we have calculated. Use the major pressure drop for the main duct as a constant to determine the duct size throughout the distribution system. Determine the total resistance in the duct system by multiplying the static resistance with the equivalent length of the longest run. Now, what is the meaning of this statement? This statement says that in the friction chart you see here, it is in the friction loss, it is in inches H2O per 100 feet. If there is a 1000 feet duct system, then we will multiply this friction loss with the 1000. The meaning of that line is this only. Okay. Now compute the balancing diameters. What is the meaning of this? Now in this case, I have already told that friction loss in this line, friction loss in this line, friction loss in this line will be same or constant. How we will achieve that? We will achieve this with the help of dampers only. We will close or open somewhere, we will close the damper, somewhere we will open the damper. Accordingly, there we will balance the pressure drop or pressure loss in the system. We will balance all the pressure pressure losses in each duct. Okay, with the help of diameter, with the help of dampers. This one is the equal friction method. Now, what are the advantages of equal friction method? The method is straightforward and simple. I think there is no confusion in that. It automatically reduces air velocity in the direction of airflow, which in turn reduce the potential airflow generated noise. You see here the volume flow rate, that will be x1 plus x2 plus x3 CFM. Now as the volume flow rate is flowing, now here x1 has gone, and in this case x2 plus x3 will go, and in this case x2 will come here, and in this case x3 will come. That means as the air is flowing, the volume flow rate of air is decreasing. In the last duct you will get the less air volume flow rate. So it automatically reduces the air velocity in the direction of air flow rate. So the volume flow rate is increasing. Now velocity will increase because you have selected the diameter of the duct already. In that case, if we have selected the constant diameter, suppose 10 inches duct is there, and flow rate is decreasing, then which parameter will decrease to accommodate or to overcome the decrease in the air flow rate? That is the velocity, because Q is equal to area into velocity. In that case, area is constant, so velocity will decrease. Okay, it automatically reduces the air velocity in the direction of airflow. So if velocity is decreasing, that's why there is no noise. If there is very high velocity, noise will be there. So that's why this is the advantage of this system. It is the most appropriate method for constant air volume system. It is very important and very beneficial method if the system is the balanced system. That means if I say this is the main duct and this one is also the 10 meter length duct, this one is also 10 meter length duct, this one is also 10 meter length duct. In the same way, how to balance? 10 meter duct will run here, 10 meter duct will run here, 10 meter duct will run here. Like this, the system will be balanced, because we have to balance the pressure. That's why this system will be helpful during the balancing, where the balance plant is there, balance system is there. Now, there is no equalization of pressure drop in the duct branches unless the system has a symmetrical layout. I have already told that the equalization of pressure drop will be very difficult, because it is very difficult to design a system which has the symmetrical layout. Okay, because symmetrical layout is somewhere it is an ideal situation, and at any cost we cannot achieve the symmetrical layout. So equalization of pressure drop we cannot achieve in this system. This is the limitation. Second, it is not recommended for VAV system, where in the duct where we are using the variable air volume system, or VAV box you can say. If used for VAV supply duct system, the terminal unit requires pressure independent PI control capability to avoid excessive flow rate when duct pressure is high. So it is not recommended for VAV system, because in VAV system dampers are there, and these dampers are controlling the volume air flow rate. Friends, VAV we will study in future video, that we will be studied in the refrigeration control part. Okay, it is not flexible and adaptable to future layout change. Now, if we have set up and plant which is equalized pressure drop, which has the equalization of pressure drop, now we have to expand the capacity, then this case will not be possible, or equalization or equal friction method will not be adaptable, or you can say that is not desirable, because it is not flexible. Okay, so this is the equal friction method. Now let's see what is the static regain method. The static regain is the process of converting velocity pressure to the static pressure. I have already told what is the velocity pressure, rho v square by 2. So in this method, when the air will flow into the duct system, what will happen? That velocity pressure or dynamic pressure will reduce. So static pressure will increase. You see here what I have written. We learned in the previous section that total pressure in a duct system is equal to the sum of the static pressure and velocity pressure. Therefore, for a given total pressure, if velocity pressure is high, then the static pressure must be low. And if static pressure, that causes the air in the duct to flow, because of the static pressure only the air is flowing in the duct, and the velocity pressure is the pressure that results from the air movement. I have already explained all these terms in my previous videos. This means that it is desirable to have a high value of static pressure compared to total pressure developed by the fan. So I think it is understood that this means that it is desirable to have a high value of static pressure compared to total pressure developed by the fan. Now, in a static regain method of duct sizing is based on the Bernoulli's equation, which states that when a reduction of velocity takes place, a conversion of velocity pressure into static pressure occurs. With this method, the duct velocity are symmetrically reduced. Duct velocities are symmetrically reduced over the length of the distribution layout, which allows the velocity pressure to convert into static pressure, offsetting frictional losses in the succeeding section of duct. In the succeeding section of duct. This means there is the same static pressure near all the branches and all the diffusers. Therefore, the system designs require little or no balancing. In this case, if the velocity is reducing, only static pressure is there, then there is no, what we call as, there is very little requirement of balancing in the system. Okay, this one is the static regain method. What are the advantages and disadvantages of static regain method? All duct sections have uniform static pressure at all branches and outlets. Therefore, simplifying outlet section and correct air quantity at each outlet. I think there is no problem in that. I think you can understand that there is a uniform static pressure in all the branches and outlets, thereby simplifying outlet selection and correct air quantity at each outlet. That means we are giving the same quantity or equal quantity at each outlet of the duct in a room. The duct system will stay in balance because the losses and gains are proportional to a function of the velocity. Therefore, it is an excellent method for designing variable air volume system. The static regain method uses less pound of sheet metal and is less noisy, because in this there is no velocity, so it is very less noisy, and there is a reduction in the velocity, or what we call as dynamic pressure loss. That's why sheet metal or what we call as extra material very requirement is very less, because if high velocity of air is there, then you have to control or you have to overcome that friction also. But in the static case, there is no air movement, then you can easily handle with the less amount of material. The meaning of this is that only. What is the disadvantage? One disadvantage might be seen in network with a large pressure drop in a section near the fan outlet. Now in this case, we are using the fan, and there is when fan is flowing, that the fan is blowing air, at that point there is a large pressure drop because velocity is high at that point. So the velocity could be reduced to a minimum within a few sections in such a way that all the duct work downstream would be sized using minimum velocity. Now another disadvantage could stem from specifying a very low minimum velocity. In that case, there is a high pressure loss where we are using the fan, and as the air is flowing in the duct, at the end of the duct there is a very less velocity, and at the inlet of a duct, or you can say at the outlet of a fan, there is a very high velocity. That's why there is a pressure loss, and at the outlet of a duct, at the end part of a duct, there will be a very minimum velocity. These are the disadvantages. ducts would then tends to be very large at the end of a long run. So if velocity is less at the end of a duct, then at that point size will be very high, because you know Q is equal to area into velocity. If velocity is very less, then area will increase. So area will increase, so diameter of a duct will increase. That's why size of the duct will increase. This is the disadvantage. So friends, in this video we have studied about the duct sizing methods. All three methods we have studied. Friends, it is the theory part only. There is no numerical in this. Just you have to understand the concept. Okay. Now in the next video we will meet and we will study about the packaged air conditioner, then inverter type AC. After that we will see the VRF system, variable refrigerant flow system. Okay friends, thanks for watching this video and have a good day. Bye bye.